we are discussing photoelasticity. So, in this in the previous class we have just introduced the photoelasticity, what it is, and we introduce with respect to different techniques that we have already learned, except the numerical technique that we have not discussed in this course. And here in this lecture essentially we will understand the basics of optics. It is basically a review of optics. So, some of which we already know. As for instance, light is an electromagnetic wave and of different wavelength and frequencies vibrating in a random direction orthogonal to the line of propagation. So, if this is a line of propagation, so if this is a line of propagation, so and this is a different direction, orthogonal means so which is perpendicular to the line of propagation. So, in this so this is a perpendicular to this line is a line of propagation, and this is a vibrating in the random direction. So, so this light between two these things which is lambda, the wavelength of light and all those things. So, we just know the relationship between the wavelength and the velocity. So, if lambda is the wavelength and f is the frequency of the vibration and c is the then lambda f is constant, which is known as the velocity in vacuum of the light. So, that is also known to us 3 into 10 to the power 8 meter per seconds. So, the wavelengths of visible spectrum, which is from 570 to 700 nanometer. So, which color it represents? So, probably in our childhood we have understood it. And this 400 to 700 range we know is the visible spectrum of the light, and this essentially its light can be defined as a radiation of electromagnetic wave, and it is human visibility range. So, visibility range. So, this is the basics of light, and so essentially it is a wave, light is a wave. So, is a wave, and so it can have it can propagate in 2, 3 or one direction. So, to start with in one direction propagation, it is a wave equation that is essentially one need to solve. So, this wave equation we will not discuss it detail here. So, but the wave equation represents the light vector, the magnitude of the light vector E, and this can be represented as the forward travelling wave and the backward travelling wave, or the right travelling wave or left travelling wave. So, this is the if x t is the forward travelling wave, and then right travelling wave x plus c t. So, these two functions are essentially represents the solution of that wave equation. So, this or sometimes it is called wave motion in the positive x direction and wave motion in the negative x direction. So, E is the light vector, x is the position along the propagation, and c is the velocity of light at vacuum, and t is the time. Now, most of the phenomena that we will be talking about here can be approximated, or most of the optical effects we will be discussing here can be approximated by the single harmonic waveform. So, that means with the forward propagation only I can express it with a harmonic function. For instance, I can write a cos some omega some a cos some term. So, here I have used 2 pi by lambda x minus c t. So, this is harmonic, and this A is the amplitude of the wave. So, now this thing we know this is very similar to the simple harmonic motion. So, now this we can A is known as the amplitude of vibration. So, if we see this is a x axis and this is e axis or the light vector, and then the constant A equals to k by j the attenuation coefficient k, sometimes it is known as the attenuation coefficient. So, this if it is a constant in case of a plane wave, and this will be I think x, this will be x. So, this k by x will be attenuation coefficient, which is dependent on x. So, k is the source of the light source. Now, this thing essentially nothing but a simple harmonic wave for us. Now, we have to know if we superpose these, because in the later part when we will study the photoelasticity, you have to know if we superpose these two simple harmonic motion, what will happen, what will be the resultant wave essentially, whether it is in the same plane or it is in the out of plane wave. Then if we superpose these two, what will happen to the simple harmonic motion. So, we all know its result from our basic physics knowledge. So, for instance, let us discuss some of the relationships that for instance, time period, which is lambda by c, you know lambda is the wavelength and c is the speed of light at vacuum, and then frequency, number of oscillation, that f is 1 by time period. So, angular frequency we know that is omega 2 pi by t, which I can write 2 pi into f, the frequency, and the wave number, which is 2 pi by lambda. So, now different representations of the wave front. So, this is the our solution of the wave equation that we have assumed, and this simple harmonic motion can be written in terms of these quantities. So, for instance, here there will be a. So, a cos 2 pi by lambda x minus c t, I can write in terms of 2 pi by lambda. I can substitute it by wave number xi, and then subsequently the angular frequency. So, finally, if there is a phase difference, so if there is a initial phase difference, so that will be delta will be there. So, this equation finally becomes this. So, where E is the magnitude, epsilon xi is my wave number, x is the propagation direction, and delta is the phase difference, and omega is my angular frequency, and t is my time. So, this is finally the solution of the simple harmonic case. Now, if I want to solve this, if I want to consider now two such cases where superposition of two plane waves in a plane, for instance, if we consider xy plane, then in this plane itself is waves are there. So, now suppose let us consider two simple harmonic motion or wave fronts, and these wave fronts having similar frequency, but different amplitude. So, this is essentially A1 is the amplitude for this E1, and A2 is the amplitude for this, for the second wave. Now, x 2 pi by 2 pi lambda x 0 plus delta 1 is a phase for light wave 1, and delta 2 is phase is for second one. So, so this I 2 pi by x 0 lambda plus 2 pi delta 1 by lambda I called phase angle associated with E1, and phi 2 is my phase angle associated with E2, and then this omega is the frequency, angular frequency, which is same for these two. So, if such two waves superpose each, if we such two waves in a plane so if I try to superpose this and try to find out the resultant wave, then it is just simply an addition. So, this addition will if I now simply add this and see what is the resulting wave, then we can simply write that A 1 cos phi 1 minus omega t, A 2 cos omega phi 2 minus omega t. So, if we just expand it in a trigonometric function and this thing, if we just expand it and then write it in a cos omega t and sin omega t form. So, this becomes A cos phi and this becomes A sin phi. So, what we assume is this quantity is essentially the A cos phi, and this is A cos phi, and this quantity if I assume that A sin phi. So, now this becomes my A cos phi minus omega t. So, the resultant magnitude is A and phase angle is phase difference is phi. So, this is again you see there are two simple harmonic waves. So, the resulting waves I can also say it is a simple harmonic wave. So, we will see this what A and phi looks like. So, this looks like simple thing. So, yes, this is the resultant amplitude and resultant phase angle. So, with this I can write that A square is this. So, A square if I now that is the cos square phi, sin square phi, and then A square can be expressed in this form after some manipulation. So, this form we it is important for us, and we will see when the photoelasticity when we will discuss the photoelasticity. So, this is the magnitude, the resultant magnitude, and this is the phase difference. So, tan phi is just this. So, we know phi 1 and phi 2, A 1 and A 2. So, we can compute tan phi, and if there is a, so essentially this is the phase difference for phi 1 and phi, and this is the phase difference for phi 2, that is the second resultant wave, second wave, and that is, so first one is blue one, second one is the brown one, and the yellow is the resultant one. So, the resultant one will have the phase difference phi. So, the amplitude will also be A for the second the resultant one. Now, in a special case when the phase difference is delta, that is phi 2 minus phi 1, if I can consider as delta, and A 1 and A 2 is equal, then we get the this, the magnitude is this, and I is the intensity, that is square of this magnitude, and the resultant I of the resultant wave in case of a light wave is very important, as the optical instrument can respond to the intensity of the light. So, when you use an optical instrument, then the intensity, there is a term called intensity of the light, and this intensity of the light is essentially I, and this I is nothing but A square. So, this here that is also with the that can also be calculated for A 1 and A 2 different, and phi 1 and phi 2 are not related case. So, the intensity of light is a very important quantity here, and this also leads to the effect of the polariscope, where we design a polariscope based on this theory. So, this in a same plane when the light propagates and the resultant wave. So, it is linear polarization. That also we will see when we consider out of plane superposition of light. So, here I stop today. In the next lecture actually we will study the out of plane polarization of the resultant light. Thank you.